Welcome to the final part of this week's online lecture. In part 7 we will continue our discussion of the diatomic vibrating rotor. There is one final detail that we need to resolve. Here is the spectrum of gaseous HCl that you may well have measured for yourselves in CM2101. Notice that at low frequencies in the P branch the lines are getting steadily further and further apart, while at high frequencies in the R branch the lines are getting closer and closer together. We want to know why this is. The rotational fine structure is becoming more crowded as we go to higher and higher frequencies. This result does not agree with our analysis in part 6, so how can we resolve this contradiction? The reason for this is due to anharmonicity. As discussed at the end of part 4, as we go to higher frequencies, the average bond length is getting longer. The potential energy well is steeper at low bond lengths, but it is shallower at larger bond lengths. This means that the average bond length is steadily getting longer as we go to higher vibrational levels. From our study of rotational spectra, we know how the bond length affects the rotational constant. The rotational constant is inversely proportional to the moment of inertia, which is itself proportional to the square of the bond length. Therefore, the rotational constant is inversely proportional to the bond length squared. If the bond length is getting larger, the rotational constant is getting smaller. So the rotational constant for a molecule in the V=1 state will be smaller than that for a molecule in the V=0 state. In the previous analysis in part 6, we assumed that it would always be the same. What happens if we don't make that assumption? And that is what we're going to do now. Let's see if we can get rid of this assumption and see what happens. So we know that the rotational constant should be affected by the vibrational quantum state. In a sense, it means that the rotational energy isn't independent of the vibrational state. It depends on the vibrational state. So the rotational and vibrational states are not truly independent of one another. They are coupled to one another. This is an expression that relates the rotational constant in different vibrational levels. So again, notice that we've got the subscript V to identify which vibrational level the rotational constant is associated with. So V could be equal to 0, 1, 2, and so we would have B0, B1, B2, etc. BE is the hypothetical rotational constant that the molecule would have at the bottom of the potential energy well. That is, when it has no vibrational energy. So the rotational constant in level V is equal to BE minus a constant alpha times V plus a half. The alpha constant is known as the interaction constant. It is generally a small positive value because, as you can see, as we go to higher vibrational energy levels, the rotational constant gets smaller and smaller. So that would be the case if alpha was a small positive value. We can rewrite the expression for the total row vibrational energy of the system in terms of the amount of vibrational energy and the amount of rotational energy. But this time we have identified the fact that the rotational term depends on the vibrational state with a subscript V. Let's have a look at how this will affect things. Once again, here are our row vibrational energy levels associated with fundamental band. Again, this is my R branch with J increasing by +1, and this is my P branch where J decreases by 1. The rotational structure in the V=0 state are associated with the B0 rotational constant, but the rotational structure in the V=1 state are associated with the B1 rotational constant, which is going to be slightly smaller. The B rotational constant is dependent on the vibrational quantum number V. To see how this will affect things, we can again write down the spectral line frequency for a transition in the P branch. This expression is almost exactly the same as the previous expression in part 6, except that rather than just writing down B, I've written down B1 for the rotational energy in the upper state, and notice that the energy in the upper state is expressed in terms of J double prime as B1 times J double prime into J double prime minus 1. And the amount of rotational energy in the lower state is B0 times J double prime into J double prime plus 1. I know what G1 minus G0 is. It is just nu E minus 2 nu E chi E, that is unchanged from before, and is of course the fundamental frequency nu 0. But this time I've got minus J double prime into B0 plus B1. Remember that before it was just 2B times J double prime, but that was assuming that B0 and B1 are the same, but they're not. They are almost the same. It is almost 2B, but it is slightly different. However, the major difference is this additional term. Before, because B1 was considered to be equal to B0, this term in J squared did not appear. This time, because B0 is slightly larger than B1, we get this additional term that goes as minus J double prime squared into B0 minus B1. It is going to be small since B0 is only slightly larger than B1, but it is going to mean taking away a steadily larger small amount. Therefore my lines in the P branch are going to get further and further apart as I go to higher and higher rotational levels. And we can do exactly the same analysis for the R branch, and it will look like this. For an R branch transition, the rotational state changes from J double prime to J double prime plus 1. Therefore, substituting for J prime is equal to J double prime plus 1, we can write an expression purely in terms of J double prime. If B0 and B1 had the same value, this expression would be identical to the previous expression for the frequencies of the spectral lines in the R branch. However, they are not the same, and the term in J double prime plus 1 all squared doesn't cancel. This term is also negative, which means that as we go to higher and higher rotational levels, we're taking away steadily more and more energy from the system, and so the lines are going to get steadily bunched together. So the formulae can be simplified by writing J instead of J double prime. So for the P branch, because B0 is slightly larger than B1, it means that the lines are going to get spread out as we go to higher initial J states. For the R branch, because B0 is larger than B1, it means that the lines are going to get closer and closer together as we go to higher initial J states. So we get a kind of convergence in the R branch. This is exactly what we saw in the gaseous HCl spectrum. The lines in the P branch are spreading out as we go to higher initial J state, and the lines in the R branch are getting closer together as we go to higher initial J state. And from this spreading out and bunching up, we can of course also determine what B0 and B1 are from this spectrum. To determine B0 and B1, we need to look closely at the rho vibrational structure. Reproduced in this graphic are the J-1, J and J plus 1 rotational levels in the V equals 0 and the V equals 1 states. On the left of this graphic we have an R branch transition from J-1 in the V equals 0 state to J in the V equals 1 state, and a P branch transition from J plus 1 in the V equals 0 state to J in the V equals 1 state. Both transitions finish in the same final rotational state. Note that the difference in energy between these two lines only depends on the rotational energies of levels in the V equals 0 state, which means that it will only depend on B0. Similarly, if we look at the two transitions on the right, they both start in the same initial rotational state, but end in different rotational states. so the energy difference between them will only depend on B1. So by taking the right combination of R and P branch lines, I can get information about B0 and B1. The transitions P of J plus 1 and R of J minus 1 have the same upper level, so therefore I can take the difference between them. I can write this down in terms of the rotational energy, and this energy is simply 2 into 2J plus 1 times B0. And if I rearrange this expression so that the energy gap is denoted by delta 0 and divide through by 2J plus 1, the result is 2B0. The expression has the same value for all values of J. A similar analysis can be done for the combination of the PJ line and the RJ line. The difference between these two transitions is denoted delta 1, and it will give us information about B1. And if we divide delta 1 by 2J plus 1, we get 2B1, and again we get the same value for all values of J. In this analysis, to determine B0 and B1, we ignored centrifugal distortion. We could have done the same analysis and taken into account centrifugal distortion. With a bit of messing around, you'll find out that what you want to plot is delta I over 2J plus 1, where the I is the 0 or 1, depending on which combination of R and P lines you want to use. It won't be a constant, but if you plot delta I over 2J plus 1 against 2J plus 1 all squared, then this is what you'll get. The intercept will be equal to 2bi minus 3di. So if you are looking at the pj plus 1 lines and the rj minus 1 lines, then I will be equal to 0, and the intercept will be 2b0 minus 3d0, and the slope of the line will just be minus d0 in this particular case. Now, of course, in practice we no longer use this rather archaic methodology. We would use standard regression techniques, similar to those I showed you in the small group tutorial using Excel to model rotational data. And with that reminder of the usefulness of Excel to perform regression, we have finished the online lectures for week 7. Next week we will continue our discussion of vibrational spectroscopy. Thanks for listening.